Kotlin Unveiled, a modern developer's journey from fundamentals to fantastic apps. Chapter 1, The Kotlin Kickoff, Why This Language Matters. Welcome, aspiring digital architect, to the exciting world of programming. You're about to embark on a journey with Kotlin, a language that's not just powerful and modern, but also incredibly fun to work with. But first, let's answer the fundamental question: why Kotlin and why now? What is Kotlin? A modern language for modern problems. Imagine programming languages as tools in a craftsman's workshop. Some are old, reliable hammers. Others are complex, multi-purpose machines. Kotlin is like a state-of-the-art, ergonomic power tool designed to make your work smoother, faster, and safer. It's a statically typed programming language, which means many potential errors are caught before your program even runs, saving you countless hours of debugging. It's also pragmatic, focusing on solving real-world development problems efficiently. But Kotlin isn't just about efficiency, it's about making programming a more enjoyable experience. It's concise, expressive, and packed with features that handle common chores for you, letting you focus on the creative aspects of building software. Who created Kotlin and why? The masters of the developer's toolkit. Kotlin wasn't born from a single academic paper or a giant tech company's internal project. It emerged from JetBrains, a company renowned for creating intelligent development tools, most notably the popular IntelliJ IDEA, an integrated development environment that many programmers consider indispensable. In the early 2010s, JetBrains developers, though highly proficient in Java, the dominant language for Android and enterprise applications, began to feel its limitations. They desired a language that offered more safety, more conciseness, and more modern features without sacrificing the vast ecosystem and performance benefits of the Java virtual machine. Their internal codebases were growing, and they sought a solution to improve their own productivity. So, instead of waiting for existing languages to evolve, they decided to build their own. They nicknamed it Kotlin after Kotlin Island near St. Petersburg, Russia, where many of their developers lived. The goal was clear: create a language that was 100% interoperable with Java, meaning Kotlin code could easily use Java libraries and vice versa, allowing for a gradual adoption without ripping out existing systems. The rise of Kotlin, from niche to Android's darling. For several years, Kotlin garnered a loyal following, appreciated mostly by backend developers and early adopters. But everything changed in May 2017 at Google I/O, Google's annual developer conference. In a landmark announcement, Google declared Kotlin a first-class language for Android development. This was a pivotal moment. Previously, Android development was almost exclusively done in Java. Google's endorsement instantly catapulted Kotlin into the mainstream, making it the preferred language for building mobile applications on the world's most popular operating system. This wasn't just a marketing ploy. Google recognized Kotlin's inherent advantages. Its conciseness meant fewer lines of code to write and maintain, leading to faster development cycles. Its built-in null safety, more on this revolutionary feature later, significantly reduced the null pointer exceptions that plagued Java applications, a source of endless headaches for developers. Since then, Kotlin's adoption has only accelerated. While Android remains a primary driver, Kotlin is increasingly used for backend development, building robust and scalable server-side applications, often as a more modern alternative to Java. Desktop applications, developing cross-platform desktop software. Multi-platform development, a cutting-edge area where Kotlin can be used to share code across Android, iOS, web, and desktop applications, drastically reducing development time and effort. Data science and machine learning. Though less ubiquitous than Python in these fields, Kotlin's performance and static typing offer compelling advantages for certain tasks. Companies large and small have embraced Kotlin. For instance, Pinterest, a visual discovery engine, famously migrated millions of lines of Java code to Kotlin, citing improved developer productivity and fewer crashes. This real-world adoption is a testament to Kotlin's practical benefits. Key advantages of Kotlin: your programming superpowers. Let's break down some of the superpowers Kotlin puts into your hands. Conciseness. Speak more with fewer words. Imagine writing a detailed story, but every sentence required you to write. This is a sentence that is conveying the information that, repeatedly. That's a bit like boilerplate code in older languages. Kotlin significantly reduces this. For example, to print the phrase, "Hello, world," to your computer screen, an older language like Java might require a structure that involves a class declaration, a method declaration, and then the printing statement, perhaps like this. Class my program, public static void main, string args, system out println, hello world. This code, with its class and public static void main and system out println terms, can feel like a lot to write just to get a message to appear. In Kotlin, the equivalent is typically just 1 or 2 lines. Fun main, println hello world. Here, the fun main part tells the computer where to start, and println directly prints your message. This conciseness means you write less, read less, and therefore have fewer opportunities for errors. This difference is analogous to comparing an older, reliable, but perhaps more cumbersome vehicle to a modern, fuel-efficient, and safe car. Both get the job done, but one is designed for a smoother, easier ride. Safety, especially null safety, no more unexpected surprises. One of the most notorious problems in programming, particularly prevalent in Java, is the null pointer exception, a dreaded error that crashes programs. It's like asking someone to fetch a tool, and they hand you nothing instead, causing your entire project to grind to a halt. Kotlin tackles this head-on with null safety. It enforces rules that make it nearly impossible for you to accidentally use a variable that holds nothing, forcing you to explicitly handle such situations. We'll dedicate an entire chapter to this revolutionary feature because it's a game changer. Interoperability, friends with Java. Think of Kotlin and Java as 2 compatible languages from the same family. Kotlin was designed to work seamlessly with existing Java code. You can use any Java library in Kotlin, and you can even call Kotlin code from Java. This means you don't have to abandon decades of existing Java resources and libraries. Kotlin builds upon them. This powerful feature allowed giant companies to adopt Kotlin gradually, 1 module at a time. The transition is smooth, not disruptive. Expressiveness. Write clearer, smarter code. Kotlin offers modern language features like extensions, delegation, and lambdas, terms we'll explore in detail later, that allow you to write code that's not just functional, but also highly readable and elegant. It allows you to express complex ideas in a straightforward manner, making your programs easier to understand and maintain. Modernity, built for today's world. Kotlin incorporates the best ideas from other modern programming languages alongside its own innovations. It's designed to run on the Java virtual machine, benefiting from its stability and performance. It's actively maintained by JetBrains and supported by Google, ensuring it stays current with the latest trends and technologies. What you'll learn in this book, your Kotlin Roadmap. This book is your comprehensive companion on the journey to becoming proficient in Kotlin. We'll start from the absolute basics, assuming no prior programming knowledge, and gradually build up your skills. Here's a glimpse of what you'll discover. Setting up your environment, how to get your computer ready to write and run Kotlin code. The foundation, understanding variables, data types, and how to make your programs perform basic operations. Controlling program flow, learning how to make decisions and repeat actions within your code. Building with functions and objects, mastering organized, reusable code blocks, and the principles of object-oriented programming specific to Kotlin. Tackling complex challenges, diving into Kotlin's powerful features like null safety, collections, and asynchronous programming with coroutines. Real-world application, getting a taste of how Kotlin is used to build practical applications, from simple command-line tools to the foundations of Android apps. By the end of this journey, you'll not only understand Kotlin's syntax and features, but also grasp the mindset of a modern, pragmatic developer. So let's open your digital workshop and begin. Chapter 2, Your First Steps, Setting Up the Kotlin Workshop. Every craftsman needs a well-equipped workshop to bring their ideas to life. For a programmer, this workshop is your computer, configured with the right tools. In this chapter, we'll set up your environment, ensuring you have everything you need to start writing and running your very first Kotlin programs. Don't worry if these terms sound daunting, we'll break them down step by step. The tools you'll need: An overview. To develop Kotlin applications, you'll primarily need three things. The JVM, Java Virtual Machine. This is the engine that runs your compiled Kotlin code. Kotlin code gets translated into something called bytecode, and the JVM executes this bytecode. Think of it as the universal translator that allows your Kotlin instructions to run on any computer. The JDK, Java Development Kit. This is a set of tools necessary for developing Java and Kotlin applications. It includes the JVM, a compiler, which translates your human-readable Kotlin code into JVM-readable bytecode, and other utilities. It's the essential toolkit for building. An IDE, Integrated Development Environment. While you can write code in a simple text editor, an IDE is like a super-powered text editor on steroids. It provides features like intelligent code completion, error highlighting, debugging tools, and project management capabilities. It's your intelligent design software and blueprint organizer. To use an analogy, your computer is the construction site, the JDK is the power tools, and IntelliJ IDEA is your specialized blueprint and design software. Choosing your IDE, our recommendation. IntelliJ IDEA. While several IDEs support Kotlin, the undisputed champion, especially for beginners, is IntelliJ IDEA. This is the flagship IDE developed by JetBrains, the creators of Kotlin. Because they built both, IntelliJ IDEA offers the most seamless and intelligent support for Kotlin development. IntelliJ IDEA Community Edition. This is the free, open-source version, perfectly sufficient for almost all the concepts in this book and a vast range of personal and open-source projects. It's highly recommended. Other options: Visual Studio Code, VS Code, with relevant extensions, or Eclipse with its Kotlin plugin are also viable, but for the best out-of-the-box experience, stick with IntelliJ IDEA. For this book, all instructions and demonstrations will assume you are using IntelliJ IDEA Community Edition. Installing the JDK, fueling your machine. Before you install IntelliJ IDEA, you need to ensure you have a Java Development Kit, JDK, installed. Since Kotlin runs on the JVM, it requires a JDK to compile and run your code. While Oracle used to provide the primary JDK, licensing changes have made OpenJDK a more common and recommended choice for most developers. There are many distributions of OpenJDK. A popular and reliable one is from Adoptium, Eclipse Adoptium. Here's a general guide for installation. Specific steps might vary slightly based on your operating system, Windows, macOS, Linux. Visit the Adoptium website, open your web browser, and go to adoptium.net. Download the latest LTS version. Look for the Download Latest LTS Release button. LTS stands for long-term support, meaning it's a stable version that will receive updates for a long time. At the time of writing, this is likely JDK 17 or JDK 21. Select the correct operating system and architecture for your computer. Run the installer. Windows, double-click the downloaded MSI file and follow the on-screen prompts. Typically, the default settings are fine. macOS. Open the downloaded PKG file and follow the installer. Linux. Often, you can install JDK via your distribution's package manager. For example, on Ubuntu or Debian, you might type sudo apt install openj17jdk in your terminal. On Fedora or RHEL, it might be sudo yum install java 17 openj. Most installers will automatically set up necessary environment variables, but it's good to know they exist. These variables tell your operating system where to find the Java tools. Installing IntelliJ IDEA, setting up your workshop. Once your JDK is installed, it's time to set up IntelliJ IDEA. Visit the JetBrains website. Go to jetbrains.com/idea. Download Community Edition. Look for the download button. On the download page, make sure to select the Community Edition as it's free. Again, choose the correct version for your operating system. Run the installer. Windows, double-click the exe file. Follow the installation wizard. You can typically accept the default settings. You might be asked to create a desktop shortcut or associate Java files, which you can choose according to your preference. macOS, open the DMG file. Drag the IntelliJ IDEA application icon into your Applications folder. Linux, extract the downloaded targz archive. You can then run the IDEA.sh script from the bin directory within the extracted folder. Many users create a desktop entry for easier access. First, launch configuration. The first time you launch IntelliJ IDEA, it will ask you about importing settings, if you had a previous version, and will present you with initial setup options, such as choosing a theme, light or dark mode, and configuring basic plugins. You can usually accept the defaults or choose your preferred theme. Your first Kotlin project. Hello Kotlin. With your workshop tools ready, let's create your very first Kotlin program. This simple program will just print a greeting to your computer screen, but it's a crucial first step. Launch IntelliJ IDEA, open the application. Create a new project. On the welcome screen, select New Project. Configure project details. Name, give your project a name, for instance, My First Kotlin App. Location, choose where you want to save your project files on your computer. Language, select Kotlin. Build system, select IntelliJ. JDK, this dropdown should show the JDK you installed. If it doesn't, click Add JDK and navigate to the installation directory of your JDK. Project template, for now you can leave this blank or select Console Application if it's an option. Click Create. IntelliJ IDEA will now set up your project. This might take a moment as it downloads necessary components. Once the project loads, you'll see a window with several panels. On the left is the Project panel, showing your project's file structure. You'll likely see a folder called src, short for source, and inside that, a file named mainkt or similar. This is where your Kotlin code will live. Now, let's write your famous Hello Kotlin message. Open the mainkt file. You should see something already present which looks like this. Fun main. Println hello world. Let me describe what you're looking at. The word fun, short for function, is how we define a function in Kotlin. A function is like a recipe or a set of instructions that the computer will follow to perform a specific task. Main is a special function. When your program starts, the computer looks for this main function and begins executing the instructions inside it. Every executable Kotlin program needs a main function as its starting point. We can think of it as telling the computer where to start reading your instructions. The empty parentheses after main indicate that it's a function. The curly braces define the body of the main function, containing all the instructions that belong to it. Println hello world is the instruction inside our main function. Println is a built-in Kotlin function that stands for printline. It takes whatever text you put inside the parentheses and quotes and displays it on the console, your computer's text output screen, followed by a new line. Now let's change the text inside the quotes from Hello World to Hello Kotlin, Fun Main. Println Hello Kotlin. That's it, your first Kotlin program is ready. Running your program. To see your program in action, find the Run icon. Look for a small green play triangle icon next to the Fun Main line in your mainkt file. Click Run mainkt. Click this icon. A small menu will appear. Select Run mainkt, or whatever your main file is named. Sometimes it is just Run. IntelliJ IDEA will now compile your code and run it. A Run tool window will appear at the bottom or side of your screen. You should see Hello Kotlin printed in the output console. Congratulations! You've successfully set up your Kotlin development environment and run your first program. This feeling of accomplishment, of seeing your code come to life, is a core joy of programming. Beyond the IDE, the online playground. For quick experiments, or if you're on a computer where you can't install software, the Kotlin Playground is a fantastic resource. Just search Kotlin Playground online, and you'll find a web-based editor where you can write and run Kotlin code directly in your browser. It's excellent for testing small snippets and sharing code. However, for serious development, a local IDE like IntelliJ IDEA is indispensable. You're now equipped with the fundamental tools. In the next chapter, we'll dive into the building blocks of any program. Variables, data types, and operators. Get ready to start speaking the language of Kotlin. Chapter 3, Building Blocks, Variables, Data Types, and Operators. Now that your Kotlin workshop is open, and you've tasted the satisfaction of running your first program, It's time to delve into the fundamental building blocks of any application. Data. Just as a builder uses bricks, wood, and concrete, a programmer uses variables to store information, data types to categorize that information, and operators to manipulate it. Introducing variables. Named containers for your data. Imagine you're baking a cake. You need flour, sugar, eggs, and milk. Instead of just having piles of ingredients lying around, you put them in labeled containers. One for flour, one for sugar, and so on. In programming, a variable is exactly like one of these labeled containers. It's a reserved space in your computer's memory that holds a piece of data, and you give it a unique name so you can refer to it later. In Kotlin, you use the keywords val or var to declare a variable. This is where Kotlin introduces a crucial concept: mutability, or the ability to change. Val for value. Use val when you want a read-only or immutable container. Once you put something in a val container, you cannot change its contents. Think of it as a sealed jar. This might seem restrictive, but it often leads to safer, more predictable code, as you're guaranteed that the data won't unexpectedly change. To declare a val variable named myMessage and store the text, "Welcome to Kotlin," inside it, you would state your intent to the computer. I want a new, unchangeable container called myMessage, and I'm putting the text, "Welcome to Kotlin," inside it. If you later tried to change myMessage to something else, Kotlin would signal an error, enforcing that the content is fixed once assigned. Var for variable. Use var when you want a mutable container, meaning its contents can be changed after it's been initialized. Think of it as an open jar where you can swap out ingredients. To declare a var variable named currentScore and initially set it to 100, then later update it to 150, you would first tell the computer, "I want a new, changeable container called currentScore, and I'm putting the number 100 inside it." Then, later in your program, you could give a new instruction. "Now, put the number 150 into the currentScore container." In this case, currentScore first holds the number 100, and then its content is updated to 150. No error here, because currentScore was explicitly declared as a variable whose contents can vary. Why two types? Kotlin encourages using val whenever possible. If your data doesn't need to change, val makes your code more robust and easier to understand. It's a core philosophy of Kotlin to favor immutability, unchangeable data, for safer programming. Data types. Categorizing information. Just as you wouldn't store flour in a liquid container, different types of data need to be handled differently by your program. In programming, data types classify what kind of value a variable can hold. Kotlin is a statically typed language, meaning that the type of a variable is known at compile time, before the program runs, which helps catch errors early. Kotlin's compiler is very smart and can often infer the data type based on the value you assign. For example, if you declare a variable and directly set its value to 30, Kotlin automatically knows that this variable is an int, which represents a whole number. Similarly, if you set a variable's value to hello, Kotlin infers it's a string meaning text. However, you can explicitly declare the type if you wish, by following the variable name with a colon and the type name. For our examples, we could explicitly state, "Let's declare a variable named age of type integer and set its value to 30, or let's declare a variable named greeting of type string and set its value to hello." Here are some of the most common built-in data types in Kotlin. Numbers, int integer, used for whole numbers, for example, 5, -100, 0. Double, used for numbers with decimal points, for example, 3.14, 0.001, -2.5. These offer high precision. If you just type a number with a decimal point, Kotlin will automatically infer it as a double. Float, also for numbers with decimal points, but generally less precise and takes up less memory than double. To tell Kotlin a decimal number should be a float and not a double, you explicitly mark the value with a small f or capital F at the end, for example, 3.14f. Long, for very large whole numbers that exceed the capacity of an int. Use suffix l or l, for example, 1,234,567,890,123 L. Short and byte, for smaller whole numbers occupying even less memory. These are used in specific performance-critical scenarios where memory optimization is paramount. Boolean represents truth values, either true or false. These are fundamental for making decisions in your programs. For instance, to indicate if a user is logged in, you might have a variable called isLoggedIn and set its value to true. Another variable has permission, could be set to false. Char character represents a single character, enclosed in single quotes, for example, 7. If you want to store a single letter, you would use a character type, such as storing the letter J in a variable called initial. String represents a sequence of characters or text. Strings are enclosed in double quotes, for example, hello Kotlin, my name is Bob. As seen previously, storing names, messages, or paragraphs is done with string variables. For instance, username could hold Alice, and welcome message could hold welcome aboard Alice. Kotlin also supports multi-line strings using triple quotes. This is great for long blocks of text or formatted output without needing special newline characters. You start and end the string with 3 double quotes. The text inside can span multiple lines as you type it. A handy function called trimIndent can be appended to remove any extraneous leading spaces that might be introduced by your code's indentation, ensuring clean formatting for your output. Operators. Performing actions on data. Operators are special symbols or keywords that perform operations on one or more values, called operands. Think of them as verbs in your programming sentences. Arithmetic operators. For mathematical calculations. The plus sign, plus for addition. If you add 5 and 3, the result is 8. The minus sign, for subtraction. 10 minus 4 results in 6. The asterisk, for multiplication. 2 multiplied by 6 results in 12. The forward slash for division. 10 divided by 2 results in 5. Important detail. If both the numbers you are dividing are integers, whole numbers, Kotlin will perform integer division, meaning any remainder will be discarded. So 7 divided by 2 would result in 3, not 3.5. To get a decimal result, at least one of the numbers must be a floating point number, a double or float. For example, 7.0 divided by 2 will result in 3.5. The percentage sign, percent for modulo, which returns the remainder of a division. For instance, 7 modulo 3 results in 1, because 7 divided by 3 is 2 with a remainder of 1. This is useful for checking if a number is even or odd, or for cyclical operations. You can store the result of an operation in a new variable. For example, if you have 2 variables, num1 holding 20 and num2 holding 3, then a variable sum storing num1 plus num2 would hold 23. A variable remainder storing num1 modulo num2 would hold 2. Assignment operators, for assigning values to variables. The equals sign is the simple assignment operator. It assigns the value on its right to the variable on its left. For example, x equals 10 assigns the value 10 to a variable named x compound assignment operators. These are shorthand ways to perform an operation and then assign the result back to the same variable. Plus equals, x plus equals 5 is a concise way of saying x equals x plus 5. Minus equals, x equals 2 is equivalent to x equals x2. Asterisk equals, x equals 3 is equivalent to x equals x3 /equals. X slash equals 2 is equivalent to x equals x slash 2. Percentage equals, x percent equals 3 is equivalent to x equals x percent 3. These are convenient for updating variable values. If you have a variable score initialized at 100, then score plus equals 50 would change its value to 150. Following that, score slash equals 2 would set score to 75. Comparison operators. For comparing 2 values. These operations always result in a Boolean value, meaning either true or false. Double equals checks if 2 values are equal. For example, 5 equals 5 is true. Hello equal to world is false. Exclamation mark equals checks if 2 values are not equal. 5 equals 10 is true. Less than 5 10 is true. Greater than 10 5 is true. Less than or equal to less or equal. 5 less or equal 5 is true. Greater than or equal to equals. 10 equals 5 is true. These operators are essential for making decisions in your program, which we'll explore in the next chapter. If you have a variable temperature holding 25, then asking is hot equals temperature 30 would result in is hot being false. Asking is room temp equals temperature equals 25 would result in is room temp being true. Logical operators, used with Boolean values to combine or modify conditions. Double ampersand, and, this is the AND operator. It returns true if both operands, the values on either side of the and, are true. If either or both are false, the result is false. So, true and untrue is true, but true and false is false. Double pipe, this is the OR operator. It returns true if at least one operand is true. It only returns false if both operands are false. So, true-false is true and false-false is false. Exclamation mark, this is the NOT operator. It inverts the Boolean value. If something is true, true is false. If something is false, false is true. Logical operators allow you to build complex conditions. For example, if you have a variable has license set to true and a variable has car set to false, then a condition can drive equals has license, and an has car would result in can drive being false, because you need both a license and a car to drive. However, if wants coffee is true and has funds is false, then can get coffee equals wants coffee has funds would result in can get coffee being true, because you want coffee, even if you don't have funds yet to buy it. String templates. Dynamic text with ease. One particularly neat feature of Kotlin that simplifies working with strings is string templates. Instead of concatenating, joining, strings and variables with plus signs, you can embed variables directly within a string using a $sign. This makes your code cleaner and more readable. Consider an older way of building a message. You declare a variable name as Sarah and age as 30. Then, to assemble a message like, "Hello, my name is Sarah and I am 30 years old," you would write something like, "Hello, my name is plus the name variable plus, and I am plus the age variable plus years old." This can become quite cumbersome and hard to read, especially with many variables. With Kotlin's string templates, it becomes elegant. You can simply write, "Hello, my name is name and I am age years old." Kotlin automatically substitutes the current values of name and age into the string. So the variable message would hold, "Hello, my name is Sarah and I am 30 years old." If you need to embed an expression, a small piece of code that calculates a value, within a string, you can wrap it in curly braces after the $sign. For example, if you have a price of 10.0 and a quantity of 3, and you want to print the total cost is $30, you could write, "The total cost is price quantity." Here, the part inside the curly braces, price quantity, is calculated first, and then its result is inserted into the string. This powerful feature significantly improves the readability and maintainability of code that deals with dynamic text. Casting and type conversions. Sometimes, you might need to convert data from one type to another. This is called type casting or type conversion. For example, you might read a number as a string from user input, because all user input is initially text, and need to convert it to an int to perform calculations. Kotlin provides a set of handy functions for this. To int, converts a string or another number type to an int. To double, converts a string or another number type to a double. To string, converts any variable to its string representation. For instance, if you have a string variable input string holding 123, you can create a new integer variable called number value by calling input string to int, which will make number value an integer with the value 123. Similarly, if you have a numeric value like 45.99, you can call to string on it to get a string variable price as string, which would hold 45.99. Be cautious with conversions. Converting a string that doesn't represent a valid number, for example, trying to convert the text, "hello," to an integer, will lead to an error in your program. Putting it all together. A simple scenario. Let's imagine a scenario where we're tracking a player's score in a game. First, we declare a mutable variable for the player's score, named player score, and initialize it to 0. We announce this. Player's initial score is 0. Next, we declare a read-only variable for points gained from picking up a coin, named coin value, and set it to 10. This won't change. Suppose the player picks up a coin. We update the player score by adding the coin value to it. Now, player score will be 10. We announce again, score after picking up a coin, 10. Then, the player completes a level, earning a bonus. We define a read-only variable level bonus multiplier as a double with a value of 1.5. This means the score should be multiplied by 1.5. To update the player score, we take the current player score, which is 10, multiply it by level bonus multiplier, 1.5, which gives us 15.0. Since player score is an int, we must convert this double result back to an int by calling to int. So, player score becomes 15. We announce, score after level bonus, 15. Now, let's check if the player has reached a high score threshold. We declare a read-only variable high score threshold as an int and set it to 100. We also create a Boolean variable, isHighScore, and set its value based on whether player score is greater than or equal to high score threshold. Since player score is 15 and high score threshold is 100, 15 is not greater than or equal to 100, so isHighScore becomes false. We announce, has player reached high score? False. Finally, the player gets an extra 90 points. We add 90 to player score. Player score was 15, so 15 plus 90 makes it 105. We announce, score after extra points, 105. We check the high score condition again. Player score is now 105, which is greater than or equal to high score threshold of 100. So our new Boolean variable now as high score becomes true. We announce, has player reached high score now? True. In this example, we used a changeable variable var for player score, unchangeable variables val for fixed values like coin value, level bonus multiplier, and high score threshold, integer and double data types, arithmetic operators, addition and multiplication, assignment operators, plus equals and simple equals, and a comparison operator, greater than or equal to, string templates, using the $sign directly with variables and with curly braces for expressions for clear output messages, a type conversion to int, to change a double result back to an int to fit into our integer score variable. Understanding how to store, categorize, and manipulate data with variables, data types, and operators is the bedrock of programming. These are the nouns and verbs of your code. In the next chapter, we'll learn how to make your programs think and decide using conditional statements and loops, building upon the data knowledge you've just gained. Chapter 4, Directing the Flow, Conditionals and Loops. In the previous chapter, you learned how to store and manipulate data using variables, data types, and operators. That's a crucial start, but a program that just stores numbers and prints fixed messages isn't very dynamic or useful. Real-world applications need to make choices, adapt to different situations, and automate repetitive tasks. This chapter introduces the control flow mechanisms that allow your programs to think and do, conditionals for decision-making and loops for repeating actions. The power of decision-making, conditionals. Imagine you're navigating a journey. You frequently encounter crossroads and have to decide which way to go based on various factors. Is it raining? Am I hungry? Do I have enough fuel? Programs face similar decisions. Conditionals are statements that tell your program to execute different blocks of code, depending on whether a certain condition is true or false. You'll recall Boolean values true or false from Chapter 3, which were the results of comparison operators like greater than or equal to. This is where those Boolean results truly shine. The if, else if, and else statements. The most fundamental decision-making tool is the if statement. It simply says, if this condition is true, then do this specific set of instructions. Let's consider a simple weather app. If the temperature is above 25 degrees Celsius, we want to tell the user it's hot. We might set up an integer variable called current temperature and assign it a value, say 28. Then, we use an if statement. We would tell the computer, if the value in current temperature is greater than 25, then print the message, it's hot outside. What if it's not hot? We can provide an alternative path using an else statement. Otherwise, meaning if the condition above was false, print the message, it's not too hot. The structure often looks like this. If a condition is true, do this specific code, else, otherwise do this other code. For example, if current temperature is 20, the first condition, current temperature greater than 25 would be false, and the program would execute the code within the else block, printing it's not too hot. You can also handle multiple possible conditions using else if. This allows you to check a series of conditions in order. For instance, you could say, if the temperature is greater than 25, print it's hot. Else if the temperature is less than 10, print it's quite cold. Otherwise, for all other temperatures, print the weather is mild. The program checks each if or else if condition in sequence and executes the first block of code whose condition evaluates to true. If none of the if or else if conditions are true, the else block, if present, is executed. A neat feature of Kotlin is that if is not just a statement that tells the program what to do. It can also be an expression, meaning it can produce a value. This allows for very concise code. For example, instead of declaring a variable and then setting its value in an if block, you could directly say, let's declare a read-only variable called weatherMessage, and its value will be take an umbrella if a condition is raining is true, otherwise it will be enjoy the sun. This makes the code shorter and often easier to read. The when expression, while if else is versatile, it can become long and cumbersome when you have many different specific conditions to check, especially when checking different values of a single variable. Kotlin offers a powerful and more readable alternative called when, which replaces the traditional switch statement found in many other languages. The when expression can match against values, ranges, data types, or even arbitrary Boolean conditions, making it incredibly flexible. Let's imagine you have an integer variable day of week where 1 means Monday, 2 means Tuesday, and so on, up to 7 for Sunday. You want to print the name of the day. Using when, you would tell the computer. When assessing the value of day of week, if it's 1, then the result is Monday. If it's 2, the result is Tuesday, and so on. If it's anything else, the result is invalid day. Val day of week equals 3, let's say it's Wednesday. Val day name equals when day of week. 1 Monday, 2 Tuesday, 3 Wednesday, 4 Thursday, 5 Friday, 6 Saturday, 7 Sunday, else invalid day. Println today is day name, output. Today is Wednesday. In this example, the when expression takes the day of week value. It then checks each line, is it 1? No. Is it 2? No. Is it 3? Yes. So it returns Wednesday, which is assigned to day name. The else branch in when is mandatory unless Kotlin can prove that all possible cases are covered. For example, if you're checking Boolean values where only true and false exist. When can also be used with ranges. For example, you might have a variable score and want to assign a grade. You could say, when assessing score, if it's in the range from 90 to 100, the grade is A. If it's in the range from 80 to 89, the grade is B. If it's in the range from 70 to 79, the grade is C. Otherwise, it's fail. Val score equals 85. Val grade equals when score. In 90.100, A score is between 90 and 100 inclusive. In 80.89, B. In 70.79, C. Else fail. Println your grade is grade, output, your grade is B. The when expression is a highly idiomatic, meaning common and preferred, way to handle multiple conditions in Kotlin, providing both power and readability. Repeating actions, loops. Automation is one of the biggest reasons we use computers. Imagine needing to print hello 100 times or process every item in a list of 1,000 customer orders. Doing this manually with individual println statements would be tedious and error-prone. This is where loops come in. Loops allow you to execute a block of code multiple times, either for a specific number of repetitions or as long as a certain condition remains true. The for loop. The for loop is primarily used for iterating over a range of numbers or elements in a collection, like a list of names or an array of items. Think of it as saying, for each item in this group, do something. Counting with for loops. If you want to count from 1 to 5, you would tell the computer. For each number I in the range from 1 to 5, print the value of I. The code would look something like for I in 1.5, println I, this would print 1, 2, 3, 4, 5. The 2 dots notation creates a range that includes both the starting and ending numbers. You can modify how for loops count. To count backwards, use down to. For each number I from 10 down to 1, print I. For I in 10 down to 1, println I would print 10, then 9, and so on down to 1. To skip numbers, use step. For each number I from 1 to 10, stepping by 2, print I. For I in 1.10 step 2, println I would print 1, then 3, then 5, 7, 9. To exclude the end number, use until. For each number I from 1 until 5, print I. For I in 1 until 5, println I would print 1, 2, 3, 4, it stops before 5. Iterating over collections. The for loop is also perfect for processing every item in a group. Imagine you have a list of names, perhaps Alice, Bob, and Charlie. To greet each one, you would say, for each name in the list of guest names, print hello name. The code for this would be conceptually like creating a list variable named guest names and assigning it the list containing Alice, Bob, and Charlie. Then for name and guest names, println hello name. This would print hello Alice, hello Bob, hello Charlie. The for loop is your primary tool for definite iteration, when you know beforehand or can determine how many times you want to repeat something, usually over a sequence of items. The while loop. The while loop is used when you want a block of code to repeat as long as a specified condition remains true. The condition is checked before each execution of the loop body. If the condition is initially false, the code inside the while loop will never run. Let's say we want to keep adding to a counter, but only stop when it reaches 10. We would start with a mutable variable count initialized to 0. Then we tell the computer, while count is less than 10, print the current value of count and then increase count by 1. Var count equals 0. While count 10, println count, count plus plus, this is shorthand for count equals count plus 1. Output 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. The loop continues as follows. Count is 0 less than 10, print 0, count becomes 1. Count is 1 less than 10, print 1, count becomes 2, and so on. When count becomes 10, the condition count 10 is no longer true, so the loop stops. The while loop is useful for situations where the number of repetitions is unknown beforehand, such as reading user input until a valid entry is provided, or processing data from a file until the end is reached. The do-while loop. The do-while loop is very similar to the while loop, with one crucial difference. Its block of code is guaranteed to execute at least once, because the condition is checked after the loop body runs. Imagine a simple program that presents a menu to the user and asks for a choice. We want to repeatedly show the menu and ask for input until the user enters a specific exit option. Even if the user immediately types the exit option, they need to see the menu once to know what to type. We would say, do the following: show the menu, ask for input, read the user's choice. Then, after you've done that, check if the choice is not equal to the exit option. If it's not, repeat the do part. Var user choice, int, do, println main menu, println 1 play game, println 2 options, println 3 exit, print enter your choice. In a real program, you'd read input here. Let's pretend user typed 3. User choice equals 3 for demonstration. Assume user immediately types 3. Println you chose user choice. While user choice equals 3 condition. Keep looping if choice is not 3. Println exiting application, goodbye. In this example, the menu and prompt are shown once. If the user then enters 3, the condition user choice equals 3 becomes false, and the loop correctly terminates after that single execution. Controlling loop execution, break and continue. Sometimes within a loop, you might want to alter its normal flow. Kotlin provides 2 keywords for this: break. The break keyword immediately terminates the innermost loop and continues execution after the loop. Think of it as an emergency stop button. If you're searching through a list of items and you find what you're looking for, there's no need to continue iterating through the rest of the list. You can break out of the loop. For example, print numbers from 1 to 10, but stop if you find the number 5. For I in 1.10, if I equals 5, break stop the loop entirely. Println. This would print 1, 2, 3, 4. The loop stops when I becomes 5. Continue. The continue keyword skips the rest of the current iteration of the loop and moves immediately to the next iteration. It's like saying, skip this one, it's not relevant, and move to the next item. For example, print only the odd numbers from 1 to 10. For I in 1.10. If I%2 equals 0. If I is even, remainder when divided by 2 is 0. Continue, skip to the next iteration. Println. This would print 1, 3, 5, 7, 9. When I is 2, 4, 6, 8, or 10, the continue statement is hit, and the println for that iteration is skipped. Both break and continue offer fine-grained control over how your loops execute, allowing you to optimize performance or simplify your logic in certain situations. Conclusion: conditionals and loops provide the fundamental power for programs to adapt, automate, and become truly useful. These constructs allow your code to come alive, making decisions and performing repetitive actions on its own. You've now learned how to ask questions and take different paths, and how to repeat tasks efficiently. We'll build on these concepts in the next chapter as we explore functions, which allow us to organize and reuse blocks of this intelligent behavior. Chapter 5, Crafting Actions, Functions and First-Class Citizens. You've now mastered the fundamental building blocks of data, variables, and their types, and learned how to direct your program's flow using conditionals and loops. But as your programs grow more complex, you'll find yourself writing similar sets of instructions repeatedly. Imagine baking several loaves of bread. You wouldn't write out the full recipe for kneading, rising, and baking every single time you wanted a loaf. Instead, you'd refer to those steps as a single, reusable process. In programming, these reusable blocks of instructions are called functions. Functions are the workhorses of your code, allowing you to organize, modularize, and simplify your programs. What is a function? Your program's mini recipe. Think of a function as a mini program or a recipe within your larger program. Just like a recipe, a function has a name. This identifies the recipe, e.g., bake bread, calculate tax. Ingredients parameters. These are the inputs the recipe needs to perform its task, e.g., flour, sugar, or in programming, numbers, text, or other data. Steps body. These are the instructions the recipe follows to process its ingredients, the lines of code inside the function. A result, return value. This is what the recipe produces, e.g., a loaf of bread. Or in programming, a calculated number, a modified piece of text, or a Boolean value. Some recipes might just perform an action without producing a tangible result, like clean kitchen. Similarly, some functions don't return a value. Why use functions? The benefits of modularity. Functions are essential for several reasons. Reusability. Write a set of instructions once and use it countless times throughout your program or even in other programs. Organization and readability. Break down a large, complex problem into smaller, manageable pieces. This makes your code easier to understand, debug, and maintain. Instead of one giant instruction list, you have a table of contents with neat, labeled sections. Abstraction. Hide complex details. When you use a function like print a message, you don't need to know the intricate low-level steps the computer takes to put text on the screen. You just need to know what the function does. Easier debugging. If there's a problem, you can identify and fix it in one specific function, rather than sifting through thousands of lines of disorganized code. Basic function syntax. Creating your first recipe. In Kotlin, you define a function using the keyword fun. Here's the general structure, explained by description. To create a function named greet, which takes no ingredients and produces no result, but simply prints, hello, Kotlin learners, you would declare funGreet. Then, inside its curly braces, you'd place the println, hello, Kotlin learners, instruction. When you call this function elsewhere in your program, Kotlin executes that print instruction. funGreet, println, hello, Kotlin learners. To use it, greet. This will print hello, Kotlin learners. Functions with parameters, inputs. Most useful functions need inputs to work with. These inputs are called parameters. You list them in parentheses after the function name, specifying both their names and their data types. Let's make our greet function more personal. We want it to take a name as an input, which will be a string text. You would declare funGreetUser name, string. Inside its body, you'd then use that name variable in a println instruction, perhaps, hello, my name is name. funGreetUser name, string. Println, hello name. To use it, greetUser, Alice, prints hello Alice, greetUser, Bob, prints hello Bob. Functions with return values, outputs. Many functions perform a calculation or process data and then give you back a result. This result is called the return value. You specify the data type of the return value after the parameters, preceded by a colon. The function's body must then include a return statement to send that value back. Let's create a function to add two numbers. It will take two integers as inputs, say A and B, and it will return a single integer as its result. You would declare fun add numbers, A, int, B, int, int. Inside its body, you'd calculate a plus B and then return that result. Fun add numbers A, int B, int, int. Return a plus B. To use it, val sum equals add numbers, 5, 3, sum will be 8. Print the sum is sum, prints. The sum is 8. Handy function features. Kotlin offers several features to make functions even more flexible and readable. Default parameters. Sometimes, a parameter often has a common, default value. Kotlin allows you to specify a default value directly in the function's definition. If the caller doesn't provide a value for that parameter, the default is used. Imagine our greetUser function, but we want to add a greeting prefix, which is usually hello. You would declare fun greetUser name, string greeting prefix, string equals hello. Inside, it would print greeting prefix name. Fun greetUser name, string greeting prefix, string equals hello. Println $greeting prefix name. To use it, greetUser, Alice, uses default hello Alice, greetUser, Bob, hi provides a custom prefix, hi Bob. Named arguments. When calling functions with many parameters, especially those with default values, it can be hard to remember the order. Kotlin allows you to use named arguments, giving them by their parameter names. This improves readability and allows you to skip parameters with default values without including placeholders. Using our greetUser function from above instead of greetUser, Bob, hi, we could call it as greetUser, name Bob, greeting prefix equals hi. This is much clearer about what each value represents. If we only wanted to provide the name and use the default prefix, we would simply call greetUser, name equals Carol. Without named arguments, this wouldn't be possible if the name parameter came first without a default. Single expression functions. For very simple functions that just calculate and return a single value, Kotlin provides an even more concise syntax. If the function's body consists of just one expression, you can omit the curly braces and the return keyword, replacing them with an equals sign. Our add numbers function can be simplified drastically. Instead of fun add numbers, A, int B, int, return a plus B, you can write fun add numbers. A, int B, int equals a plus B. Kotlin figures out the return type automatically here, so you could even omit int after the parameters and just write fun add numbers. A, int B, int equals a plus B. This makes the code super compact and readable for simple operations. Functions as first-class citizens. This concept is one of Kotlin's most powerful features. In Kotlin, functions are first-class citizens. This means they can be treated just like any other data type, such as integers or strings. Specifically, it means you can assign functions to variables. You can store a function in a variable as if it were a number or a piece of text. Pass functions as arguments to other functions. A function can take another function as one of its inputs. Return functions from other functions. A function can produce another function as its output. This might sound abstract, but it unlocks incredible flexibility and enables powerful programming paradigms. Lambda expressions, functions without names. When functions are first class, you often need to create small, simple functions on the fly without giving them a formal name. These are called lambda expressions, or just lambdas. They are like instant, anonymous mini recipes that you define right where you need them. For example, imagine you have a list of numbers and want to process each one. If you only need to define a simple operation like double the number, just once for that specific list, you might use a lambda instead of a full function definition. We won't go into the detailed syntax yet, but understand that lambdas are how you express these on-the-fly functions. Higher-order functions, functions that manipulate functions. When a function takes other functions as parameters or returns a function, it's called a higher-order function. These are master recipes that can take other recipes as ingredients or produce new recipes as their output. For instance, Kotlin has a built-in filter function which takes a list and another function, a lambda, as input. The lambda tells filter what condition to use for deciding which items to keep in the list. This lets you write very flexible and powerful data processing code. Extension functions, adding superpowers to existing types. Another incredibly useful feature related to functions in Kotlin is extension functions. These allow you to add new functions to an existing class or type without having to modify its original source code. Imagine you have a basic string text in Kotlin. You might decide you want to add a new function called capitalize first letter to all strings, even though string doesn't natively have it. You can define an extension function that does exactly this. It's like saying, from now on, whenever I have a piece of string, I want to be able to call capitalize first letter on it. You are essentially giving new superpowers to existing types. This greatly enhances code readability and allows you to create highly expressive domain-specific languages, DSLs, within Kotlin. Conclusion: functions are the cornerstone of well-structured and maintainable programs. They allow you to define repeatable actions, manage complexity, and build your applications piece by piece. The concept of functions as first-class citizens and the related features like lambdas, higher-order functions, and extension functions are what give Kotlin much of its power and elegance. Mastering functions is a critical step in becoming a proficient Kotlin developer. In the next chapter, we'll dive into how Kotlin structures data and behavior together using object-oriented programming principles. Chapter 6. Blueprints and Builders, Object-Oriented Kotlin. In the previous chapters, we've explored how to handle individual pieces of data and control the flow of your program. But real-world applications often deal with complex entities that have both characteristics data and behaviors actions. Think of a car. A car has a color, a model, a speed characteristics, and it can start, stop, accelerate, and brake behaviors. Grouping these together makes our code more organized and easier to manage. This is the essence of object-oriented programming, OOP, and Kotlin is a powerful, modern language built on these principles. What is object-oriented programming, OOP? OOP is a programming paradigm that organizes software design around objects rather than functions and logic. An object can be defined as a data field that has unique attributes and behaviors. It's a way of structuring programs into self-contained modules that interact with each other. To understand OOP, let's break down its core concepts using an analogy. Imagine you're designing a car assembly plant. Instead of just having a pile of parts and a list of instructions, you'd want blueprints, classes. Before you build any cars, you need a blueprint. This blueprint describes what a car is. It has wheels, an engine, seats, doors. It also describes what a car can do. It can drive, turn, break down. This blueprint is called a class. A class is like a template or a cookie cutter. Actual cars, objects. Once you have the blueprint, you can build many individual cars from it. Each car is a unique instance of the car blueprint. One might be a red sedan, another a blue truck. These individual instances, created from a class, are called objects. An object is a real, tangible entity created from the class blueprint. Characteristics, properties. For each car, there are specific details. For the red sedan, its color is red, its model is sedan XYZ, its current speed is 0. These characteristics, defined in the blueprint but holding specific values for each object, are called properties, also known as attributes or fields. Behaviors, methods, functions. What can the car do? It can start, accelerate, brake, turn. These actions that an object can perform are called methods or member functions. In Kotlin, classes are how we define these blueprints, and objects are the actual items created from them. Defining a class in Kotlin, your first blueprint. Let's create a simple car class. We would define class car. Inside its curly braces, we would list its properties, like color, which is a string, and speed, an int initialized to 0. Then we would define its methods, functions like start, which prints car started, and accelerate, amount. Int, which increases speed by the amount and prints the new speed. Class car. Var color, string. Var speed, int equals 0. Fun start. Println car started. Fun accelerate amount. Int speed plus equals amount. Println accelerating, current speed, speed km/h. Fun break, speed equals 0. Println brakes applied, car stopped. Creating objects instances, building cars from the blueprint. Once you have your car blueprint class, you can create as many car objects as you need. Each one will have its own separate color and speed. To create a new car object, you use the class name followed by parentheses. Val myCar equals car creates a new car object and assigns it to myCar. Val another car equals car creates another distinct car object. Now myCar and another car are entirely separate entities. You can access their properties and call their methods using dot notation. We can set the color of myCar to red. Then we can call the start method on myCar. After that, we can call the accelerate 30 method. For another car, we could set its color to blue, start it, and accelerate it by 50. myCar.color equals red. myCar start. myCar accelerate 30 acceleration. Current speed 30 km/h. Another car.color blue. Another car start. Another car accelerate 50 acceleration. Current speed 50 km/h. Notice how myCar and another car each keep track of their own speed independently. This encapsulation of data and behavior within objects is a core benefit of OOP. Constructors, equipping your blueprints. When you create a new object, you often want to give it some initial values. For instance, when assembling a new car, you might want to specify its make and model right away. This is done using a constructor. A constructor is a special function within a class that is called automatically when an object of that class is created. Kotlin has a concise way to define a primary constructor directly in the class header. Class car val make, string val model, string var color, string var speed, int equals 0. Fun start, println $make, model started, its color is color. Fun accelerate amount, int, speed plus equals amount. Println accelerating make, current speed, speed km/h. Now when you create a car object, you must provide these initial values. Val mysedan equals car, Toyota, Camry, silver. Mysedan start, prints, Toyota Camry started. Its color is silver. Mysedan accelerate 60. The parameters in the primary constructor, make, model, color, automatically become properties of the car class. Since make and model are val, their values cannot be changed after the object is created. Color is a var, so it can be changed later. Inheritance, building on existing blueprints. OOP allows for code reuse through inheritance. Imagine you have a general vehicle blueprint. Instead of creating entirely new blueprints for car, motorcycle, and truck, each starting from scratch, you can say, a car is a vehicle plus some car-specific things. This means a car blueprint automatically gets all the characteristics and behaviors of a vehicle, and then you can add or override its own specific features. The original class is called the parent class or superclass, and the new class that inherits from it is called the child class or subclass. In Kotlin, classes are, by default, final, meaning they cannot be inherited from. To allow a class to be inherited, you must mark it as open. Let's define an open vehicle class. Open class vehicle, val name, string, val wheels, int, open fun drive. Mark is open to allow overriding in subclasses. Println, $name is driving on wheels. Class car make, string model, string color, string. Vehicle, $color make model 4. Car inherits name and wheels from vehicle, and adds its own properties methods. Init block runs when object is created. After primary constructor, println, a new color make model car has been assembled. Override fun drive. Override the drive method for car. Println, the name car speeds along the highway. Fun honk. Println beep. Beep. Class motorcycle make. String model, string vehicle, $make model 2. Override fun drive. Println, the name, motorcycle roars down the road. Fun do wheelie. Println, whoa, doing a wheelie on the name. To use these, val myCar equals car, Honda, Civic, red. myCar drive calls the overridden drive method for car. The red Honda Civic car speeds along the highway. myCar honk calls car's specific method, beep beep. Val my motorcycle equals motorcycle Harley, Davidson. My motorcycle drive calls the overridden drive method for motorcycle. The Harley-Davidson motorcycle roars down the road. My motorcycle do wheelie, calls motorcycle's specific method. Whoa, doing a wheelie on the Harley-Davidson. Inheritance promotes code reuse, all vehicles drive, and helps model real-world relationships. Polymorphism, many forms, one action. Polymorphism, meaning many forms, is a powerful concept directly related to inheritance. It means that objects of different classes can be treated as objects of a common parent class, even though they may implement a method, like drive. In different ways, you can call that method on any of them without knowing their exact specific type. Consider a list of vehicle objects. Some might be car objects, others motorcycle objects. Val vehicles equals list of my car, my motorcycle, a list of vehicle objects. For vehicle and vehicles, vehicle drive, each vehicle knows how to drive itself appropriately. This would print, the red Honda Civic car speeds along the highway. The Harley-Davidson motorcycle roars down the road. Even though my car and my motorcycle are different types, they both respond to the drive command in their own specific way. This is polymorphism in action, simplifying code that interacts with diverse but related objects. Encapsulation, keeping things tidy and safe. Encapsulation is the practice of bundling data, properties, and methods that operate on the data into a single unit, the class. It also means restricting direct access to some of an object's components and instead requiring interaction through publicly exposed methods. Imagine a car's engine. You don't directly manipulate the pistons, but rather interact through the accelerator pedal. This is achieved using visibility modifiers, public default, accessible from anywhere. Private, accessible only within the class itself. Protected, accessible within the class and its subclasses. Internal, accessible within the same module, a collection of files compiled together. By making properties private and exposing them through public methods, often called getters and setters in other languages, though Kotlin handles these concisely, you can ensure that an object's internal state is always valid and consistent. Abstract classes and interfaces, defining contracts. Sometimes you need a blueprint that defines a common set of behaviors but doesn't fully implement them. Abstract classes. An abstract class is a class that cannot be instantiated directly. You can't create an object of its type. It can contain abstract methods, which must be implemented by subclasses and non-abstract methods. Think of it as a partially completed blueprint that requires its children to fill in the missing details. Interfaces. An interface defines a contract. It specifies a set of methods that a class must implement if it claims to adhere to that interface. An interface only declares methods and can have abstract or non-abstract properties. A class can implement multiple interfaces, allowing for flexible behavior composition. Interfaces are like a checklist of required features. If you are a flyable object, you must have a takeoff method and a land method. Both abstract classes and interfaces are powerful tools for designing flexible and extensible object-oriented systems in Kotlin, allowing you to define clear roles and responsibilities in your code. Conclusion: the power of OOP in Kotlin. Object-oriented programming, with its concepts of classes, objects, properties, methods, inheritance, and polymorphism, provides a robust framework for building complex and maintainable software. Kotlin embraces OOP fully, offering concise and modern syntax to implement these principles. By organizing your code into these reusable, sensible units, you unlock a new level of power and clarity in your programming journey. In the next chapter, we'll dive into one of Kotlin's most celebrated features related to safety, its approach to handling null values. Chapter 7, the null-safe revolution. Embracing type safety. In the previous chapters, you've built a solid foundation. Understanding data with variables, controlling program flow, crafting reusable actions with functions, and structuring your code with object-oriented programming. Now, we arrive at a feature that fundamentally sets Kotlin apart from many other languages, especially its predecessor, Java, its robust approach to null safety. This might sound like a technical detail, but it addresses a problem so pervasive and costly that it's often referred to as the billion-dollar mistake. The problem with nulls. The billion-dollar mistake. What is null? In programming, null is a special value that means no value, nothing, or absence of a value. It's like a variable that has been declared but doesn't point to any actual data in memory. The billion-dollar mistake was a term coined by Sir Tony Hoare, the computer scientist who introduced null references in the ALGOL language in 1965. He later regretted it, stating that it has led to innumerable errors, vulnerabilities, and system crashes. These errors often manifest as null pointer exceptions, NPEs, or null reference errors, which are runtime errors that occur when a program tries to use a variable that holds null as if it were a valid object. Imagine you're trying to perform an action on a piece of data, like calculating the length of a customer's name. If the customer's name variable is null, meaning no name was ever provided or retrieved, and your program tries to find its length, it simply won't know what to do because there's nothing there. The program then crashes with an NPE. These crashes are notorious for being hard to track down, appearing only during specific, often unexpected, execution paths and causing system failures. Kotlin's solution: nullability in the type system. Kotlin addresses this problem head-on by making nullability part of its type system. This means that the Kotlin compiler explicitly knows which variables are allowed to hold null and which are not. This forces you, the programmer, to deal with potential null values at compile time when you write your code, rather than allowing a surprise crash at runtime. The core idea is simple: non-nullable by default. By default, all variables in Kotlin are non-nullable. This means a variable cannot hold null. If you try to assign null to a non-nullable variable, the Kotlin compiler will immediately show you an error, preventing the problem before your program even runs. For example, if you declare a variable named name and intend for it to hold a string, you would declare it simply as val name. String equals Alice. You will get a compile time error if you try to later assign name equals null. This ensures that whenever you access name, you know it contains a valid string. Nullable types. If you genuinely need a variable that can hold null, because, for example, a user's phone number might be optional or a database query might return nothing, you explicitly declare it as nullable by adding a question mark after its type. For instance, to declare a variable named phone number that can be a string or null, you would declare it as var phone number. String equals null. Now, phone number can either hold a string like 555 to 1234 or the null value. The compiler will now enforce that whenever you try to use phone number with an operation, like finding its length, you must first safely check if it is not null. Working safely with nullable types. Kotlin provides several elegant tools to work with nullable variables without risking NPEs. Safe call operator. This is one of the most commonly used tools. When you have a nullable variable and you want to call a method or access a property on it, you use the safe call operator. Imagine you have a nullable variable name, string. When you want to find its length, you'd write name, length. If name is not null, the length property is accessed, and the result is the length of the string. If name is null, then the entire expression name, length simply evaluates to null. It does not crash your program, so if name is Bob name, length would be 3. If name is null name, length would be null. The result of the safe call itself is always nullable. Elvis operator. The Elvis operator, named because it resembles Elvis Presley's iconic hairstyle sideways, provides a default value when a nullable expression evaluates to null. It's like saying, if this value is null, then use this value instead. You use it in conjunction with the safe call. For example, if you want to print the length of a nullable name, but show if name is null, you'd write val length equals name, length 0. If name is Alice name, length is 5, so length becomes 5. If name is null name, length is null. The Elvis operator then kicks in and length becomes 0. This makes handling default values very concise. The let function. Sometimes you want to perform a block of operations only if a nullable variable is not null. The let function is perfect for this. It takes a block of code, and if the nullable variable is not null, the code block is executed, with the non-null value available inside the block as the implicit variable it. If you have a nullable email address, string, and you want to print a confirmation message only if an email address exists, you could write email address, let. println confirmation email sent to it. If email address holds user@example.com, it prints confirmation email sent to user@example.com. If email address is null, nothing is printed. This chains well with the safe call operator and provides a clear, scoped way to handle non-null scenarios. Not null assertion operator. This operator is the equivalent of yelling at the Kotlin compiler. I know this variable is not null at this point. Trust me and treat it as non-nullable. It converts any nullable type to a non-nullable type. Example: val namelength equals name length. If name is not null, this works perfectly, and name length gets the length. If name is null at this point, your program will crash with a null pointer exception. Yes, Kotlin reintroduces the NPE here, but only when you explicitly tell it to trust you. Use with extreme caution. You should only use when you have external evidence or logic that guarantees a value won't be null, but the compiler can't figure it out. It's often seen as a last resort and a potential code smell, indicating that a safer approach, or let, might have been overlooked. Practical implications and benefits. Kotlin's null safety dramatically improves the reliability of your code. By forcing you to address nullability early in the development cycle, the compiler acts as a static analysis tool, catching potential runtime errors before they even occur. This leads to fewer crashes, the most obvious benefit. Your applications will be more stable and robust. Cleaner code. You spend less time writing defensive if variable equals null checks everywhere because the intelligent operators handle it concisely. Improved readability. When you see you immediately know that the variable can be null and needs special handling. If there's no, you know it's guaranteed to be non-null. Increased developer confidence. You can be more confident that your code won't blow up unexpectedly due to missing values. Think of it like building a bridge. In languages without built-in null safety, you might construct a bridge only to find out during a test drive that a crucial support beam was missing, resulting in a collapse. In Kotlin, the planning and construction tools themselves shout warnings if you forget a beam, forcing you to reinforce it before the bridge is ever used. Null safety is a cornerstone of Kotlin's pragmatism and a major reason for its enthusiastic adoption, particularly in areas like Android development where application stability is paramount. Mastering these concepts means you're writing safer, more resilient software, avoiding the proverbial billion-dollar mistake in your own projects. Chapter 8: Data Wrangling. Collections and Beyond. So far, we've focused on handling single pieces of data using variables. But real-world applications rarely deal with just one item at a time. Imagine managing a user's shopping cart, a list of student grades, or the positions of thousands of game characters. You need ways to store and manipulate groups of data. This is where collections come into play. Collections are fundamental structures that allow you to group multiple items together. Kotlin provides a rich set of collection types, along with powerful functions to process them. Why collections? The power of groups. Think of collections as specialized containers designed to hold multiple items. Each type of container is best suited for different situations. Do you need to keep items in a specific order, like a grocery list, where the position matters? You'd use one type of collection. Do you need to ensure all items are unique, like a list of registered usernames, where duplicates are not allowed? You'd use another type. Do you need to look up information quickly by a key, like a dictionary where you look up a word to find its definition? There's a collection for that too. Using collections simplifies data management, makes your code cleaner, and allows you to perform operations on entire groups of data efficiently. Common collection types in Kotlin. Kotlin offers several core collection interfaces and their implementations. The three most common are lists, sets, and maps. Before diving into them, it's crucial to understand a key Kotlin distinction: mutability. Immutability versus mutability. Just like with single variables, Kotlin strongly emphasizes immutability in collections by default. Immutable collections, read-only. These collections cannot be changed after they are created. You cannot add, remove, or modify items within them. They are fantastic for ensuring data consistency and safety, especially in multi-threaded environments, which we'll touch on later. When you want to change an immutable collection, you actually create a new collection with the desired modifications. These are created using functions like list_of, set_of, and map_of. Mutable collections, changeable. These collections can be modified after creation. You can add, remove, or update their elements. Use these when you need to dynamically change the contents of your group of data. These are created using functions like mutable list_of, mutable set_of, and mutable map_of. Kotlin's encouragement of immutability is a strong safety feature, helping you avoid accidental data modifications that can lead to bugs. 1. Lists, ordered sequences of items. A list is an ordered collection of items. This means that the position or index of each item matters, and items can be accessed by their index. Lists can contain duplicate elements. Think of a to-do list, a sequence of song titles in a playlist, or a series of temperatures recorded over time. Creating a list. To create an immutable list of names, you would say, let's make a list named names and put Alice, Bob, and Charlie in it. This uses the list_of function. If you need to add or remove names later, you'd make a mutable list_of. Val immutable names list of Alice, Bob, Charlie. Var mutable names equals mutable list of David, Eve. Accessing elements. Elements in a list are accessed by their index, starting from 0. Immutable names get 0 would give you Alice. You can also use square brackets like immutable names 1, which would give you Bob. Adding removing mutable lists. For mutable names, you can add Frank, which would append Frank to the end. You can also remove David to remove David from the list. Iterating. You can easily loop through all items in a list using a for loop, which we learned about in Chapter 4. For instance, to print every name in your immutable names list, you would say, for each name in immutable names, print the name. 2. Sets, unique collections of items. A set is an unordered collection of unique items. This means that if you try to add an item that already exists in the set, it won't be added again, and the set will remain unchanged. The order of elements is generally not guaranteed. Think of a list of unique subscribers to a newsletter or a collection of tags associated with an article, where order doesn't matter and duplicates are meaningless. Creating a set. To create an immutable set of numbers, you would say, let's make a set named unique numbers and put 1, 2, 3, and 2 in it. Because sets only store unique items, the final set would only contain 1, 2, and 3. You'd use set_of or mutable set_of. Val unique numbers equals set_of 1, 2, 3, 2 will result in 1, 2, 3. Var mutable guests equals mutable set_of John, Jane. Adding removing mutable sets. For mutable guests add John would have no effect if John is already there. Mutable guests add Mike would add Mike. Checking for presence. Sets are very efficient for checking if an item is already present. Unique numbers dot contains 3 would return true. 3. Maps, key value pairs. A map, also known as a dictionary or associative array, is a collection that stores data as pairs of key and value. Each key must be unique, and it maps to a single value. You use the key to retrieve its associated value. Think of a phone book name is the key, number is the value, or a user profile, username is the key, user's age is the value. Creating a map. To create an immutable map of country codes to country names, you would say, let's make a map named country codes where US maps to United States and GB maps to United Kingdom. You'd use map_of or mutable map_of. Val country codes equals map_of US to United States, GB to United Kingdom. Var user scores equals mutable map_of Alice to 150, Bob to 200. The to keyword is a special Kotlin construct to associate a key and value. Accessing values. You retrieve a value by providing its key. Country codes, US, would give you United States. Note that accessing a key that doesn't exist will return null, remember null safety. Adding updating mutable maps. For user scores Charlie equals 180 would add a new entry. If you then say user scores Bob equals 250, Bob's score would be updated. Iterating. You can loop through a map to get both its keys and values. For instance, to print each user and their score from user scores, you would say, for each user and score pair in user scores, print $user has score points. Powerful collection functions. Data wrangling with ease. Kotlin's standard library provides a rich set of higher-order functions, functions that take other functions as arguments, which we touched upon in Chapter 5, that make working with collections incredibly expressive and efficient. These functions allow you to transform, filter, and process your data with minimal code. Here are a few widely used examples. Filter creates a new collection containing only the elements that satisfy a given condition. Imagine you have a list of numbers, 1, 2, 3, 4, 5, 6. You want to get only the even numbers. You would apply filter to numbers using a condition. Is the number divisible by 2 with no remainder? The result would be a new list containing 2, 4, and 6 map. Transforms each element in a collection according to a given function, creating a new collection of the transformed elements. If you have numbers 1, 2, 3, and you want to double each number, you would apply map to numbers using a transformation. Multiply the number by 2. The new list would contain 2, 4, and 6. For each. Performs an action for each element in the collection. If you have a list of names, Alice, Bob, you want to print a greeting for each. You would apply for each to names and the action. Print hello, followed by the name. Find or first or null. Returns the first element that satisfies a given condition, or null if no such element is found. If you have numbers 10, 20, 30, 40, and you want to find the first number greater than 25, you would use find with the condition. Is the number greater than 25? It would return 30. Count returns the number of elements that satisfy a given condition. From numbers 1, 2, 3, 4, 5, 6, you want to count how many are even. You would use count with the condition. Is the number divisible by 2 with no remainder? It would return 3. These are just a few examples. Kotlin's collection API is vast and powerful, allowing you to perform complex data manipulations in a declarative style. You describe what you want to achieve, rather than how to achieve it step by step. This often leads to more readable and maintainable code. Beyond basic collections, sequences, while filter and map are great, they create new intermediate collections for each operation. For very large collections or chains of multiple operations, this can be inefficient. Kotlin offers sequences, created with asSequence, as an alternative for more optimized processing. Think of a list as a complete river already flowing. When you filter or map it, you make a clone of the entire river and then modify the clone. A sequence is like a lazy river. Operations on a sequence are performed element by element only when the final result is actually needed. This is called lazy evaluation. If you have a huge list and want to filter it, then map the results, then count them. With a list, it would first create a filtered list, then a mapped list, then count the final mapped list. With a sequence, it would take one item from the original list, filter it, map it, then count it, then move to the next item. No intermediate lists are created. For most day-to-day tasks with reasonably sized collections, list operations are perfectly fine. But when performance for very large datasets or complex pipelines becomes a concern, sequence provides a powerful optimization. Conclusion: collections are indispensable for managing groups of data in any programming language, and Kotlin's rich set of types and powerful functions make data wrangling a breeze. Understanding the distinction between mutable and immutable collections, and knowing when to use lists, sets, or maps are crucial skills. The expressive power of Kotlin's collection functions will allow you to write clean, concise, and efficient code for manipulating your data. This mastery will prove invaluable as you tackle more complex problems, which often involve massive amounts of information. Chapter 9: Conquering Asynchronicity. A gentle dive into coroutines. So far, all the code we've written has been synchronous and blocking. This means that when your program executes a line of code, it must fully complete that line before moving on to the next. If that line involves a long-running operation, like fetching data from the internet, reading a large file from disk, or performing a complex calculation, your entire program freezes or blocks until that operation is done. Imagine ordering coffee at a busy shop. Synchronous, you order. The barista takes your order, then stops everything else until your coffee is made. Only after your coffee is handed to you does the barista start taking the next customer's order. This leads to long queues and an unresponsive experience. Asynchronous, You order. The barista takes your order, gives you a number, and then immediately starts taking the next customer's order. While one coffee is brewing, another is being ordered, and another is being served. This is much more efficient and keeps the line moving. In the world of software, a frozen application means a bad user experience. For example, if an Android app freezes while waiting for network data, the user might think it crashed. Handling these long-running tasks asynchronously, meaning not immediately, doing something else in the meantime, is crucial for building responsive and efficient applications. Historically, handling asynchronicity involved complex mechanisms like callbacks, futures, or reactive streams, which often led to difficult-to-read and maintain code, often called callback hell. Kotlin offers a revolutionary solution to this problem: coroutines. What are coroutines? Lightweight concurrency. Coroutines in Kotlin provide a powerful and concise way to write asynchronous, non-blocking code that looks and feels like ordinary synchronous code. They simplify asynchronous programming by allowing you to write code that pauses its execution and resumes later, without blocking the main program thread. Lightweight. Coroutines are much lighter than traditional threads, which are a fundamental unit of execution managed by the operating system. You can launch thousands of coroutines without performance issues, whereas launching too many threads can exhaust system resources. Suspendable. The key concept is suspending functions. A suspend function is a function that can be paused and resumed later without blocking the thread it's running on. When a suspend function encounters a long-running operation, like a network request, it can suspend itself, allowing the underlying thread to do other work. Once the long operation completes, the suspend function is resumed from where it left off, on the same or a different thread. Structured concurrency. Kotlin coroutines promote structured concurrency, a paradigm where the lifetime of a coroutine is bound to a specific scope. This helps manage the lifecycle of asynchronous operations, ensuring that all background tasks are properly canceled when they are no longer needed, preventing common issues like memory leaks or rogue background processes. The suspend keyword, your asynchronous signal. To make a function capable of pausing its execution without blocking the underlying thread, you simply mark it with the suspend keyword. Suspend fun, fetch data from network. String, simulate a network request that takes 2 seconds. Delay, 2000. This is a special suspend function provided by Kotlin coroutines. Return data from the internet. The delay function here is a suspending function. When delay is called, fetch data from network suspends its execution for 2 seconds. The thread that was running fetch data from network is now free to do other work, keeping your application responsive. After 2 seconds, fetch data from network automatically resumes from where it left off. You can only call suspend functions from within other suspend functions or from within a coroutine builder, which we'll discuss next. This ensures that the compiler knows where potential suspension points are and can manage the asynchronous flow correctly. Coroutine builders, launching your asynchronous tasks. To start a coroutine, you need a coroutine builder. The two most common builders are launch and async. Both require a coroutine scope to define their lifecycle. Launch, used when you want to start a new coroutine that performs a task and doesn't return a result. Think of it as fire and forget, or do this work in the background. Launch is typically used for tasks like updating a UI, logging, or saving data to a database without needing to wait for the result. Import kotlinks.coroutines. You'll need to import the coroutines library. Fun main equals run blocking. Run blocking is a coroutine builder used primarily for main function in examples. Println main program starts. Launch, start a new coroutine in the background. Println coroutine started. Fetch data in process, call a suspend function. Println coroutine finished. Println main program continues immediately. Suspend fun fetch data in process. Println fetching data. Delay 1000, simulate network delay. Println data fetched and processed. When you run this, the output will likely be main program starts. Coroutine started. Main program continues immediately. Fetching data. Data fetched and processed. Coroutine finished. Notice how main program continues immediately appears before the data fetching is done. This clearly demonstrates non-blocking behavior. Async, used when you want to start a coroutine that does return a result. It returns a deferred object, which is essentially a promise that a result will be available in the future. You can use the await function on a deferred object to get its result. Await is itself a suspending function, so it will pause the current coroutine until the result is ready. Async is excellent for performing parallel operations and then combining their results. Import kotlinks.coroutines. Suspend fun fetch user details. String. Delay 1500. Return user details loaded. Suspend fun fetch order history. String. Delay 1000. Return order history loaded. Fun main equals run blocking. Println loading user dashboard. Val user details equals async fetch user details. Start fetching user details asynchronously. Val order history equals async fetch order history. Start fetching order history asynchronously. Await will suspend this coroutine run blocking until the results are ready. Println user details await. Println order history await. Println dashboard fully loaded. The output would be loading user dashboard. 1 second delay as order history finishes. User details is still running. User details loaded. This is printed after 1.5 seconds from start. Order history loaded. If order history await was called first, it would print after 1 second. Then wait for user details await. Dashboard fully loaded. Here, both fetch user details and fetch order history start almost simultaneously. The program waits for both to complete before printing dashboard fully loaded, but it does so efficiently by fetching them in parallel. Coroutine context and dispatchers. Where does the work happen? When you launch a coroutine, it runs within a coroutine context, which includes a coroutine dispatcher. The dispatcher determines which thread or thread pool a coroutine uses for its execution. Dispatcher's main or dispatcher's main immediate for UI updates on platforms like Android. Coroutines launched with this dispatcher run on the main thread, which is typically where UI operations must happen. Requires specific platform setup. Dispatchers.io for I/O-bound operations like network requests, reading from disk, or database access. This dispatcher uses a shared pool of threads suitable for these blocking operations without blocking the main or computational threads. Dispatchers.default for CPU-bound operations that consume a lot of processing power, like heavy calculations, sorting large lists, or image processing. It uses a shared pool of threads equal to the number of CPU cores. Dispatchers unconfined, a special dispatcher that starts the coroutine in the caller's thread, but then resumes it in whatever thread the suspending function used. Generally not recommended for production code due to unpredictability. You can specify the dispatcher when launching a coroutine. Launch dispatchers.io. This code will run on an I/O thread. Good for network disk operations. Val data equals fetch data from network. With context, dispatcher's main. Switch to the main dispatcher to update UI if on Android desktop. Println UI updated with data. The with context function allows you to temporarily switch the dispatcher for a specific block of code within a coroutine, which is incredibly useful for ensuring that UI updates happen on the correct main thread after a background task completes. Structured concurrency and coroutine scope. Managing lifecycle. One of the most important concepts in Kotlin coroutines is structured concurrency. This means that coroutines are organized in a hierarchy, resembling a tree structure. A parent coroutine can launch child coroutines. When the parent coroutine or its scope is canceled, all of its children are automatically canceled as well. This prevents common bugs like memory leaks, long-running background tasks continuing after the component that launched them, like an Android activity, has been destroyed. Abandoned jobs, coroutines running indefinitely without anyone waiting for their results, wasting resources. Coroutine scope is a key component here. It defines the life cycle of coroutines. On Android, for example, you typically create a coroutine scope that is tied to the lifecycle of a screen, e.g., view model scope or lifecycle scope. When the screen is destroyed, its scope is canceled, and all coroutines launched within that scope are automatically canceled too. Error handling in coroutines. Error handling in coroutines often involves standard Kotlin try-catch blocks, but it's important to understand how exceptions propagate. Exceptions in child coroutines generally propagate up to their parent. For coroutines launched directly by launch, unhandled exceptions will crash the application by default unless specific exception handlers are configured. For async, the exception is contained within the deferred object and will only be thrown when a wait is called. Conclusion: towards more responsive applications, Kotlin coroutines provide a paradigm shift in how we write asynchronous code. They remove the complexities and boilerplate associated with traditional asynchronous patterns, allowing developers to write clean, sequential-looking code for non-blocking operations. By understanding suspending functions, coroutine builders like launch and async, and the importance of dispatchers and structured concurrency, you gain a powerful toolset for building highly responsive, efficient, and robust applications, from mobile apps to backend services. This is a topic that can fill entire books, but this gentle introduction should give you enough to appreciate their revolutionary power and start your asynchronous journey. Chapter 10: Building Bridges. Generics, Type Parameters, and Type System Deep Dive. In the preceding chapters, we've explored Kotlin's core functionalities. From basic data handling to structured programming, object-oriented principles, null safety, and even asynchronous operations. Now, we'll delve into a more advanced yet crucial aspect of Kotlin that enables highly flexible, reusable, and type-safe code. Generics and a deeper understanding of Kotlin's type system. Generics allow you to write code that works with different types of data without sacrificing type safety. This is like building templates for classes and functions, where you specify the exact data types to be used later, making your code adaptable to various scenarios. The problem generics solve: type safety without repetition. Imagine you need to create a container that can hold a single item. If you make a container specifically for string objects, it might look like this. Class string container val value string. Now, if you need a container for int objects, you'd have to write almost identical code again. Class int container val value int. This leads to code duplication. What if you wanted a list that could hold any type of object? While you could use a general type like any Kotlin's equivalent of Java's object, the root of the class hierarchy, this sacrifices type safety. If you retrieve an item from a list of any objects, the compiler won't know its precise type, forcing you to use unsafe typecasts or runtime checks, which can lead to errors. Generics provide a solution by allowing you to define a type parameter when you declare a class or a function. This type parameter acts as a placeholder for a specific type that will be provided when the class or function is actually used. Introducing generics, type parameters as placeholders. Let's revisit our container example using generics. We'll use a type parameter, conventionally t for type, to represent the type of value the container will hold. To create a generic container class called box, which can hold any type of item, you would declare class box t val item t. The t after the class name signifies that box is a generic class and t is its type parameter. Inside the class, item is of type t class box t val item t. Now, when you create an instance of box, you specify the actual type. Val string box equals box, hello generics, t becomes string. Val int box box, 123, t becomes int. Val boolean box equals box, true, t becomes boolean. The compiler now knows that string box holds a string, int box holds an int, and boolean box holds a boolean. If you try to assign an int to stringbox.item, you'll get a compile time error, preserving type safety. Generic functions, making functions type agnostic. Functions can also be generic. For example, a function that swaps two elements in a list, regardless of the element's types, can be made generic. To create a general function swap that takes a list of any type t and two int indices and returns nothing, you would declare fun t swap list. Mutable list t index 1, int index 2, int, unit followed by the swapping logic. Fun t swap list, mutable list t index 1, int index 2, int, val temp equals list index 1, list index equals list index 2, list index 2 equals temp, val numbers equals mutable list of 1, 2, 3. Swap numbers 0, 2, numbers is now 3, 2, 1. Val words equals mutable list of apple, banana, cherry. Swap words 0, 1 words is now banana, apple, cherry. The t before the function name, indicates that it's a generic function. Type constraints, setting boundaries for generics. Sometimes you want a generic type to be any type, but sometimes you need it to be a subtype of a specific class or implement a certain interface. This is where type constraints come in. You can restrict the types that can be used as type arguments for a generic parameter using the operator. For example, if you want a function sum of numbers that works on a list of numbers, you need to ensure t supports arithmetic operations. You can restrict t to be a subtype of number. To create a function sum of numbers for a list of type t, where t is a subtype of number and returns a double, you would declare fun t, number sum of numbers, list t, double and then add up the numbers, converting each to a double fun t, number sum of numbers, list t, double. Var sum equals 0.0. For number and numbers, sum plus equals number to double. Return sum. Val int list equals list of 1, 2, 3. Println sum of int list, prints, 6.0. Val double list equals list of 1.5, 2.5, 3.0. Println sum of double list, prints, 7.0. Sum of list of hello, compiler error. String is not a number. This enforces that any type used for t must be a number or one of its subclasses, int, double, float, etc., allowing you to safely call to double on them. Variance. In and out, covariance and contravariance. This is a more advanced topic in generics, often considered one of the trickier aspects, but it's essential for truly understanding Kotlin's type system and how its collections work. It deals with how subtyping behaves with generic types. Out covariance. When you declare a type parameter t as out t, e.g., interface source out t, it means t can only be produced by the class or function, not consumed. If there is a subtype of b, then source A can be considered a subtype of source B. Think of list out t, you can get items out of a list, but you can't put items into it if it were purely read-only. If you have a list cat, where cat is a subtype of animal, it makes sense to treat list cat as a list animal because you only ever get cat objects from it, and every cat is an animal. In contravariance, when you declare a type parameter t as in t, e.g., interface consumer in t, it means t can only be consumed by the class or function, not produced. If A is a subtype of B, then consumer B can be considered a subtype of consumer A. This is less intuitive. Imagine a comparator in T interface that has a function to compare two objects of type T. If you have a comparator animal, it can compare any two animal objects. It can also compare two cat objects because cat is an animal. So, a comparator animal can effectively serve as a comparator cat. This means comparator animal is a subtype of comparator cat, which is the opposite of the out direction. Kotlin's type system manages this complexity to provide powerful and safe mechanisms for working with collections, especially read-only ones. List is covariant in its type parameter, and mutable ones, which are invariant. You'll most commonly encounter out in Kotlin's standard library. Reified type parameters, bridging runtime and compile time. Another powerful and unique feature in Kotlin generics is reified type parameters. In many languages with generics, type information about generic parameters is erased during compilation. This is called type erasure. This means you can't check the actual type of T at runtime. Kotlin, however, allows you to mark a type parameter as reified for inline functions. This preserves the type information at runtime, making it possible to do things like isChecks, checking if an object is of a certain type, or casting to T. For example, imagine you have a list of mixed types and you want to filter out only elements of a specific type. Without reified, this would be very difficult. Inline fun reified T list any filter as instance. List T, val result equals mutable list of T. For item in this, if item is T, this is check is possible because T is reified. Result add item. Return result. Val mixed list equals list of apple 123, true, banana 456. Val strings equals mixed list filter as instance string. Strings becomes apple, bananas. Val numbers equals mixed list filter is instance int. Numbers becomes 123, 456. The inline keyword is necessary for reified type parameters, and it essentially tells the compiler to copy the function's code directly into the call site, thus preserving the type information. Deep dive into Kotlin's unified type system. Kotlin has a unified type system. This means that unlike some other languages where primitive types, like int, boolean, are distinct from object types, in Kotlin, everything is an object. Numbers, characters, and booleans are all objects. This has several implications. Nullability. As you learned in Chapter 7, null is handled consistently across all types, whether they are reference types or what would be considered primitive types in other languages. Methods on primitives. Since even int and boolean are objects, you can call methods on them directly, like 123 to string or trueNot. Interoperability. Sometimes, when interacting with Java, Kotlin will automatically unbox these types for performance, but from a developer's perspective, you always treat them as objects. The root of the Kotlin class hierarchy is any. Every class in Kotlin implicitly inherits from any. If a class doesn't explicitly declare a supertype, any is its direct supertype. Any has three member functions: equals, hashcode, and toString. Conclusion. Generics, type parameters, and the subtleties of Kotlin's type system are powerful tools for creating robust, flexible, and reusable code. They allow you to write algorithms and data structures that operate on various data types while maintaining strict compile-time type safety. Understanding concepts like type constraints, variants, in and out, and reified type parameters will enable you to write more advanced and idiomatic Kotlin code, making your programs more adaptable and resilient to future changes. While these concepts might seem complex initially, their mastery unlocks a significant level of programming power. Chapter 11, Real-World Kotlin, From Console Apps to Android Backend Basics. So far, we've walked through Kotlin's fundamental features, from variables and control flow to object-oriented programming, null safety, coroutines, and generics. These are the bricks and mortar of any Kotlin application. But where does Kotlin actually live in the real world? How do these concepts come together to build tangible software? This chapter will bridge that gap, showing you how Kotlin expands beyond simple examples to power various types of applications. We'll touch upon command line, console, applications, mobile apps, Android being the prominent example, and backend services, server-side programming. The JVM, Kotlin's universal runtime. A key reason Kotlin is so versatile is its primary target, the Java Virtual Machine, JVM. As discussed in Chapter 2, Kotlin compiles to bytecode that runs on the JVM. This means Kotlin can leverage the vast, mature, and efficient Java ecosystem, including its enormous collection of libraries, tools, and established deployment practices. This provides Kotlin with immense power and adaptability without having to build everything from scratch. This JVM compatibility is Kotlin's superpower, allowing it to build bridges across many different application domains. 1. Console applications, quick tools and utilities. Console applications, also known as command line programs, are perhaps the simplest type of application to build. They don't have a graphical user interface, GUI, but interact with the user via text input and output in a terminal window. They are perfect for simple scripts and automation, automating repetitive tasks, processing data files, or generating reports. Utility tools, small programs that perform specific functions like converting units or parsing logs. Learning and prototyping, a great starting point to test ideas and algorithms without the overhead of a full GUI framework. How Kotlin powers them. We've already been writing console applications. Every fun main, println, hello Kotlin. Program you've run is a simple console application. You use regular println for outputting text and readline, for reading user input, which we haven't extensively covered yet, but it's the counterpart to println for input. For example, a simple command line calculator could read two numbers and an operator, then use when expressions to perform the calculation and print the result. This demonstrates how basic data handling, control flow, and functions form the backbone of practical tools. Anatomy of a simple Kotlin console app. Example: a simple interactive greeting. Fun main. Print, please enter your name. Val name equals readline. Reads a line of text input from the user. If name, null and a name is not blank, safe check for null and empty input. Println, hello name. Welcome to your first interactive Kotlin app. Else, println, hello, mysterious stranger. Please tell me your name next time. You could then add loops for continuous interaction and functions to organize different commands. This interaction, while basic, forms the foundation of many powerful command line utilities. 2 Android applications. Kotlin's flagship domain. Kotlin's rise to prominence is largely due to Google's official endorsement as the preferred language for Android app development. If you've used an Android phone, you've likely used apps built with Kotlin. Why Kotlin for Android? The reasons are largely those we discussed in Chapter 1. Conciseness. Less boilerplate code required compared to Java, leading to faster development and fewer bugs. Null safety. Significantly reduces the infamous null pointer exceptions that have historically plagued Android apps, leading to more stable applications. Seamless Java interoperability. Android traditionally uses Java. Kotlin can use all existing Java libraries and frameworks in Android, allowing for gradual migration and leveraging existing knowledge. Modern features. Coroutines for easier asynchronous programming, essential for UI responsiveness. DSLS, domain-specific languages, for building UIs, and other modern language features make development more efficient and enjoyable. Basic structure of an Android app, Kotlin perspective. An Android application is made up of various components, primarily activities, which represent a single screen with a user interface, and fragments, modular parts of a UI within an activity. These are typically written in Kotlin, and they interact with Android's powerful SDK, Software Development Kit. When you build an Android app, you're primarily designing UIs, defining what the user sees using XML files for layout, and then connecting them to your Kotlin code. Handling user interaction, responding to button clicks, screen touches, and other inputs using Kotlin functions. Managing data, fetching data from networks or databases, often using coroutines, processing it, and displaying it. Managing app lifecycle, responding to events like the app coming to the foreground or going to the background. While building a full Android app is beyond the scope of this book, understand that the Kotlin principles you've learned, variables, classes, functions, null safety, coroutines, are directly applied. User interfaces are often represented as objects, and their actions trigger functions written in Kotlin. Kotlin extensions in Android. Kotlin's extension functions, from Chapter 5, are heavily used in Android to add convenient methods to existing Android classes, making the code more readable and concise. 3 Backend services, powering the cloud. Beyond mobile apps, Kotlin is gaining significant traction in backend development, the server-side code that powers websites, mobile apps, by providing data and other cloud services. Why Kotlin for backend? Performance. Running on the JVM, Kotlin enjoys excellent performance characteristics suitable for high-traffic servers. Conciseness and readability. Leads to faster development of APIs and easier maintenance of complex business logic. Spring framework support. Spring Boot, one of the most popular Java frameworks for building enterprise-grade backend services, has first-class support for Kotlin. This makes it incredibly easy to start building scalable web applications and microservices. Coroutines for concurrency. Backend services often need to handle many concurrent requests efficiently without blocking. Kotlin coroutines are a perfect fit for building highly scalable and reactive server applications. Type safety reduces runtime errors, making server applications more reliable. Common Kotlin backend frameworks. Spring Boot. The most popular choice, leveraging Spring's extensive ecosystem, but with Kotlin's modern syntax. Ktor, a lightweight, asynchronous web framework built specifically for Kotlin by JetBrains, ideal for microservices and REST-TFL APIs. Vertex, Micronaut, Quarkus, other modern JVM frameworks that also offer excellent Kotlin support. Example, simplified Ktor concept. Imagine a backend service that provides product information. You would define a product class using Kotlin's data classes, a special type of class for holding data, often used for representing information going to from web services. Then, using a web framework like Ktor, you'd write a function that, when a specific web address is accessed, retrieves product data, perhaps from a database. using coroutines for non-blocking access, and sends it back to the requesting app or website. Simplified Ktor root concept. This code would be part of a larger Ktor application setup. Example of a data class used for backend API models. Data class product val_id. Int val_name, string val_price, double. This would represent a web endpoint products. It uses features like coroutines, suspend fun, and collection processing, which you've learned. Suspend fun get products endpoint, list product. In a real app, this would fetch from a database or another service. Using a suspend function for non-blocking I/O. Delay 500, simulate database lookup delay. Return list of product 1, laptop, 1200.00, product 2, mouse, 25.50, product 3, keyboard, 75.00. When a client, like an Android app, makes a request to this endpoint, it would receive a list of product objects. This demonstrates how familiar Kotlin concepts translate directly to building powerful web services. For Kotlin Multi-Platform, KMP, sharing code across ecosystems. This is where Kotlin truly stretches its wings. Kotlin Multi-Platform Mobile, KMP or KMM, allows you to write common business logic once in Kotlin and share it across Android and iOS applications. Even further, Kotlin Multi-Platform can target web with Kotlin JS and desktop with Kotlin JVM and Compose Multi-Platform. How it works. KMP uses different Kotlin compilers for different platforms. Kotlin JVM for Android, backend, desktop. Kotlin native for iOS, macOS, watchOS, tvOS. Kotlin JS for web frontend. WebAssembly, WASM, for performant web applications. You write your core logic, data models, networking business rules, in a common Kotlin module. This module then compiles to the appropriate bytecode/native code for each platform. The UI layer, which is very platform-specific, is still written using native technologies, e.g., Compose Multi-Platform for Android desktop, Swift UI for iOS, React HTML for web. This approach drastically reduces code duplication between platforms, leading to faster development, fewer bugs, and more consistent behavior across different versions of your application. It's truly building bridges. Conclusion. Kotlin is everywhere, from humble command-line scripts to powering the world's most popular mobile operating system, and from robust cloud services to innovative cross-platform solutions, Kotlin has proven its versatility and power. The foundational knowledge you've gained in this book directly applies to these diverse domains. As you continue your Kotlin journey, you'll find that these real-world applications are simply sophisticated orchestrations of the variables, functions, objects, and control flows you've already learned to master. The next step is to explore more advanced features and continue your ongoing learning adventure with this fantastic language. Chapter 12. Beyond the Basics, Advanced Features and Your Kotlin Journey Ahead. Congratulations! You've embarked on an incredible journey through the world of Kotlin. From understanding its fundamental building blocks and structuring code with object-oriented programming, to navigating the complexities of null safety, efficiently handling data with collections, conquering asynchronicity with coroutines, and building flexible systems with generics, you've gained a solid foundation. You've also seen how Kotlin powers real-world applications across various platforms. This final chapter serves as a look forward, briefly touching upon some more advanced Kotlin features and concepts that you might encounter and want to explore next, as well as guiding you on how to continue your development journey. More advanced Kotlin features to explore. Kotlin is a rich language, continually evolving. Here are a few notable features and areas you might delve into next. Delegation by keyword. Kotlin makes it easy to implement the delegation design pattern, which is a powerful alternative to inheritance for code reuse. Instead of inheriting behavior, an object can delegate that behavior to another helper object. The by keyword is used for class delegation and delegated properties. This allows you to write cleaner, more flexible code and avoid issues associated with deep inheritance hierarchies. Delegated properties. A fantastic use case of delegation is for properties. For instance, by lazy is a common example where a property's value is computed only on its first access. Other examples include by delegates observable, to perform an action whenever a property changes, or by delegates not null, for properties that cannot possibly be null after initialization, even if formally defined as mutable. Sealed classes and interfaces. These are powerful tools for modeling restricted class hierarchies. A sealed class, or interface, allows you to define a set of nested classes that are the only possible subclasses. This is particularly useful in conjunction with when expressions, as it allows the compiler to perform exhaustiveness checks. If you've covered all possible subclasses in your when expression, you don't need an else branch, making your code safer and more robust. This is excellent for representing states, events, or distinct options in your application. Inline classes, value classes. A newer feature designed to improve performance by allowing you to create custom types that wrap a single value, without the overhead of creating a new object on the heap. This can be useful for type safety, e.g., data class user ID, val value, string, while avoiding runtime performance penalties often associated with such wrappers. Operator overloading. Kotlin allows you to redefine the meaning of operators, like plus, asterisk, slash, equals equals, etc., for your custom classes. This lets you write code that is more intuitive and mathematical when working with domain-specific objects. For example, you could define how two vector objects are added together using the plus operator. Coroutines deep dive, channels, flows, select. While we had a gentle introduction to coroutines, the ecosystem is vast. Channels provide a way for coroutines to communicate by sending and receiving streams of data. Flows, built on top of coroutines, flows are a very powerful way to handle asynchronous streams of data that emit multiple values over time. They are particularly useful for reactive programming patterns, where you react to data as it arrives, e.g., UI events, sensor readings, continuous network updates. Select allows a coroutine to wait for the first of multiple suspend functions to complete. Annotations. While you might not write custom annotations immediately, understanding them is crucial. Annotations are metadata that you can add to code elements, classes, functions, properties, etc., to provide additional information that can be processed by tools or frameworks. Common annotations include @deprecated, to indicate a piece of code that should no longer be used, or annotations used by frameworks like Spring, @REST controller, @getMapping, or Android, @composable for Jetpack Compose. Reflection. Reflection allows your program to inspect and modify its own structure and behavior at runtime. For example, you could write a program that lists all the methods of a given class or even invokes a method by its name. While powerful, reflection should be used judiciously as it can reduce type safety and performance. Your Kotlin journey ahead, where to go from here. Learning Kotlin is a continuous process. Here's how you can continue to deepen your knowledge and hone your skills. Practice, practice, practice. The best way to learn is by doing. Small projects. Start building small applications. A simple calculator, a to-do list app, a basic game like tic-tac-toe, or a weather forecast tool. Algorithms and data structures. Implement classic algorithms and data structures in Kotlin. This will solidify your understanding of both programming concepts and Kotlin's features. Online code challenges. Websites like LeetCode, HackerRank, or Advent of Code offer coding challenges that help you practice problem-solving with Kotlin. Specialize in a domain. Kotlin thrives in several areas. Choose one that excites you and dive deeper. Android development. The official Android development documentation is an excellent resource. Explore Jetpack Compose for modern UI development. Backend development. Learn Spring Boot with Kotlin or explore Ktor. Build REST APIs, connect to databases, and understand cloud deployment. Kotlin Multiplatform Mobile, KMM Multiplatform. Start building your first shared logic for Android and iOS. This is a booming area. Desktop development. Explore Compose Multiplatform for building native desktop applications. Read and analyze open source code. Look at well-written Kotlin projects on GitHub. See how experienced developers use Kotlin's features, structure their projects, and solve common problems. Engage with the community. Join Kotlin user groups, online forums, and communities, like Reddit's r/Kotlin or Discord channels. Follow Kotlin experts and JetBrains on social media. Attend local meetups, conferences, or online webinars. Explore the standard library and beyond. Kotlin's standard library is incredibly rich. Spend time with the documentation to discover more collection functions, utility functions, and patterns. Look into popular third-party libraries that solve specific problems, e.g., networking, JSON parsing, testing. Stay updated. Kotlin is an evolving language. Keep an eye on official announcements from JetBrains, read their blogs, and check for new releases and features. Consider certifications, optional. While not necessary for many roles, some may find value in certifications, e.g., from JetBrains, to formalize their knowledge. Final thoughts. Kotlin is more than just a programming language. It's an ecosystem designed for developer productivity and happiness. Its modern design, safety features, versatility across platforms, and strong community support make it an excellent choice for new and experienced developers alike. You've taken the essential first steps, laying a robust foundation. Remember the analogies: we used variables as containers, functions as recipes, classes as blueprints, coroutines as efficient baristas. These mental models will continue to serve you well. The journey of programming is one of continuous learning, problem-solving, and creation. Embrace the challenges, celebrate the successes, and most importantly, have fun building remarkable things with Kotlin. Go forth and code. The world is waiting for your next great application.